All right, everybody, welcome to our first Cornell and UBS seminar in AI and data of the year. I'm really happy to have Eghbal Rahimikia, who's from the University of Manchester and is, covering a topic that is exactly in our little niche here, which is frontiers and applications of AI in finance. And we've included in the chat room some links to his paper as well. There's also a portal and a website that really will help you, get started with these concepts. So anyways, without further ado, Eghbal, you can take the floor, and I'm very excited to hear your presentation.
Yeah, thank you. Hi all, thank you for the invitation. And today I'm going to talk about our new study, revisiting time series foundation models in finance. Uh, One of the reasons we moved to this area was the fast pace we see these days in developing different models. And it's moving to other areas too. It's not just large language models. We see agents. We see time series models that they are using the same architecture or some similar architectures to large language models for time series forecasting. So we moved to this area because we saw there are many models coming. Most of the companies, later we talk about that, they are making new models and they are competing with each other. The same thing we see in large language models. We have benchmarks. Every few months they release a new model. Google, Salesforce, we have some models from Amazon. And actually, these models are becoming, they're adding it to their, infrastructure, and companies that are using it for financial forecasting. And we saw that in finance, especially hedge funds, investment banks, they started using these models, or at least showing some interest. So we moved to this area to see how exactly these models are working, because one of the dangers we see now in the market with this surge in AI tools, that people, without properly checking models, testing the models, they start using them. And this is not good, because most of the competition now, like in large language models, is based on some benchmarks. It shows some aspects of the performance, but when we move to the real world, like AI in finance, in trading, it should be, assessed clearly in a structured way to understand how these new models that we see every few weeks, a new of them, are working. So our focus was staying away from developing a new model and put it there, and mostly looking at the current architectures we have, that the millions of people, they downloaded them and they are using, if you check Hugging Face. And big companies like Google, Amazon, IBM, even Ant Group, each company has its own model now. They are promoting them, and they call it time series foundation models, or TSFM. We had these models before from years ago. These are just focusing on making really large models and putting a lot of data there and making a general model to forecast everything. But with the surge we saw in large language models, the architecture changed. They became quite similar to the architectures we see in large language models now. And of course, for doing something like that, we spend, so much resources. We had some support from the government. Latest investment in UK is Embark AI server. Later, I talk about that, because finally, because they are a branch of large language models, using them, and for us that we wanted to use the same architectures for developing our own models, it was quite computationally intensive. Later, we talk about that, how much we spend in resources, how much time we spend, and whether it is a good idea to focus on these type of the models in future or not. So the paper is available online. We just released it last year. It was around, I think, December. And it was quite interesting. This paper already downloaded for thousands of the times. And again, we are going to have a revision. So this is the first, preliminary draft. Definitely there are going to be errors. It's quite long. 140 pages. The new version is going to be shorter, but in the first version, we try to present everything, all the details that when people they want to implement, they want to test, they see it clearly in the paper. So motivation. We have many models outside, many papers that are focusing on financial time series forecasting. It's a good area because we have massive data. Data is noisy. The signal is quite small compared to the noise. And it's a really good environment for comparing different new models we have in the market now because of these features. We already applied many ML models. We have many papers that are using ML models for trading. All of them, they are telling we are the best. We reached this Sharpe ratio. From simple models, from linear models to really complex models, we see a lot of studies doing that. And also we see some people that are using large language models, but so far nobody focus on in a proper way, in a comprehensive way on time series foundation models that is specifically designed for time series forecasting, as I said, based on the same architectures. But there are many problems here. The first problem here is that we don't have a benchmark. We need to make our own tests, our own benchmark. One of the problems we have in the literature, because most of them are coming out from the companies, is that they made their own benchmark and they are competing based on that. This is not our playground. We want to make a financial benchmark. We need to have a proper group of models and see whether these models are able to beat or those models in our horse race or not. So this is the first thing we are focusing on that. Second, we are not just focusing on a statistical forecasting. Many models, they may reach really good R-squared, really good accuracy, directional accuracy, that we present them. But when we move to the economic performance, they may not perform well. So we put both of them together like all the studies we have in finance. And also we come not just focusing on testing these models. We have different levels. We start with zero shot, fine tuning, and after that we pre-train these architectures with our own data. Because this is the same thing we do with other models. When we want to estimate an OLS regression, when we want to train a neural network, that's the way we do it. So we use off-the-shelf models, but at the same time, we extract the architecture and make our own models to see when we are really fair, and we use our own data and we compare these models, which one is winning. So these are the goals and motivations we have. What is TSFM? It is huge. Most of these models, they have millions or billions of parameters. They, like large language models, they are pre-trained from mixture of data. So the target is not just finance. When they release these models, they pre-train the models based on financial data, weather, and even synthetic data, large, because they are huge. We don't have that much time series data involved, like the data we have as text to train, large language models. They try to add synthetic data based on different distributions too. Even they are not trained by the same time scale. Usually they are minutes, seconds, monthly, and these models on paper are able to forecast any frequency or any data. This is the same concept we have in large language models. Mixture of the data, different combination, even text, even anything comes to the a model, and model is able to learn everything. And now we have ChatGPT and other bots and agents. Same idea here. And we want to see whether this works for finance or not. Clearly, in benchmarks, they work very well. They are competing with each other. Every day we have a model coming up. But what about in finance, in a trading, environment? So we focus on zero shot. Zero shot, it means just using the models they release. We show, the results for over 15, 16 generations of the models they release. They say if the models is not working, you can fine-tune it, like fine-tuning large language models to make it better. We did it with financial data. And more importantly, we did pre-training too. It means we use, as I said, the architectures and use our own data for pre-training. We focus on two models. These are the most popular models we have in the market, Kronos model and TimesFM. But later we extend these models, especially for zero shot, to 14 models to see how these models are performing in zero shot. But for pre-training, we choose two most popular models. The way they process data is quite interesting. Kronos model looks at the version 1, usually. The new versions are a bit different. We use the base version for 2024. They are looking at the time series data, like text data. They say, okay, this number, that number, let's set some ranges. This is the first range from 1 to 3. This is the second range from 3 to 5. If the data, this number is in this range, I set, token number 1, ID 1. If it is in this range, ID 2. So it's exactly translating numbers as text and passing to a same architecture we have in large language model. This is a concept. Of course, the ranges we are talking about that is quite tight here and small, and there are some, ways we set in these ranges. But this is the concept behind that. We have TimesFM model. The concept is a bit different. They try to consider range, the blocks of data or patches of data and passing it to the embeddings of time series. They try to break the time series to different patches and see, okay, this patch can be a series, or it's like the group of tokens we pass to the model. Another patch we pass to the models. Another idea, but quite similar. This one is becoming more popular and more competitive these days. Most of the architectures are using this, structure. So these are two types of the models we see in the market that
So,
they
Eghbal,
started.
can I
Yeah.
ask you a quick question? Could you simplify a bit, like what are the inputs and the outputs of these models? So, for example, do I give it, let's say, a time series of Apple stock between,
Mhm.
2020 and today, and is that the input, and what do I get out of the model? I'm
It
curious.
should be, it's a forecasting model. It should be output. The thing you are feeding to the model, the expected output is the next day, return. The same thing we did in this paper. So as I said, the input is exactly numbers, and the output, we can set how many days we want forecast for the input, and it can be, 1, 2, 3, 4, 5. We can set it 20 days, 30 days. We can set whether it is weekly, monthly, or forecast. These are the base models we are focusing on that. They are univariate. Latest architectures that are coming to the market now, they are multivariate, but we are focusing on just univariate environment now.
Okay.
So we just pass the past history of anything. It can be returns, it can be prices, and we expect the model's output to be the forecast. And the other important thing is that these models, they make distribution. They don't make the exact output, And the output is usually we are averaging between these values, the same thing we did in this paper. But the good thing is that we can have potentially the distribution of the output. Like large language models, the next forecasted word, it's a list of words. It's actually a distribution, and the model is choosing the most probable one, like ChatGPT. Same thing here. It makes a distribution, and usually we calculate the average between expected outcomes or forecasts from the output. So this is the whole story behind the models for the people that are not familiar with, time series foundation models. So if you want
So
to focus on the sub,
we can think of this a little bit like a Monte Carlo simulation, except without an actual, how shall I
yeah.
say, statistical constraint like Brownian motion or something
Yeah,
like that.
yeah.
Okay.
And it is like off-the-shelf model. This is the thing they claim, that this is a model, you can use it anywhere you want. So we have access to the waste, but nobody cares about that. This model is designed for this company, works very well, and now it's in the production and people are using. So this is the comparison in the size. These are the models we tested in this paper. So it's not all the models in the market. Some of the models actually, they come here. They are much larger. So these are our benchmarks that later I talk about, that from Lasso, Reach, PCR, Light, GPM, and we had some approximate number of parameters. And here we are moving to the TSFMs, much, much larger. We talk about near 1 billion parameters in a model, when we want to pre-train for the largest model. Here, 500 million. So in terms of machine learning models, we are talking about really, really large models compared to the conventional models we used to use in finance. Big difference. But again, question, do we really need this size or not? We are going to answer this one in this work. So why it's hard, those sizes? It needs high computational cost, because even for testing these models, you need to use GPUs. It's not working on CPU. And for pre-training, it becomes more challenging. For pre-training these models, they use billions of samples, and synthetic data. And more importantly, we are talking about time series forecasting. We should not make a single model with the latest data and apply it on past information. This may bring lookahead bias. We need a strict chronological training, which means for each year we are going to have one model. Otherwise, it's not a fair comparison. When we want to forecast 2005, we need a model that just saw or pre-trained with data until end of 2004. In practice, for a small models, it's quite simple. We estimate a linear regression again, but here we need to pre-train the whole neural networks, whole TSFM again for each year for new data. And we did it to make everything fair and comparable with the benchmark models. As I said, a statistical performance, economic performance, zero shot, means just using the models. Fine tune, it means use our data to tune those weights a bit, but still we use their models to fine tune. Pre-train, it means making our own models based on their architectures. Written forecasting. The case is quite simple. We make a single model for entire market, for US market, with all data we have. Later, we are going to extend it to global market and everything. For now, just US market. Each year, end of each year, we make one model with all excess returns we have in the market. The data is daily, just daily data, because it was better to move to monthly data, but it's not that much data. We need so much data for pre-training these models. Daily data, just excess returns, univariate. We pre-train or estimate or train all benchmark models per year. We make portfolio later and compare the models. So the structure is quite simple and conventional here. This is the data we have. These are the data we use for making US. We have different types of models. The models that they just use US data, the models that they use global data, all 94 countries we have access to, all excess returns around the world. They came together and made one model. So for now, we start with US. As you see, for each year we have one model. The data starts from 1990. So from 1990 to 2000, we make one model, 2001, 2, and use it for forecasting the next year. This is happening for both conventional models, linear models, and for the benchmark models. We are going to talk about that. Number of stocks or securities, maximum is reaching to 62,000. For international, it is reaching to 204,000. It means using all data. We have everything, all excess returns in a single model. Still, compared to the models they developed, these models are much, much smaller in scale of the data we use. But let's see how it works. You see the data here. I'm showing what data usually we have access to from CRIS, from WRDS. We have access to the data from 1990, 10, 90 to 20. But as you see, the size of data is quite small, especially when we want to make a global model. First, as I said, I just use US data, but later I focus a model that use more data. Here we set the beginning of the data 1990 that we use for pre-training the models, estimating all the models, because the quality of the data before this was they were missing information than the other things. So 1990 is the beginning. 2000 is the first model we have. Use it for forecasting 2001. We make a new model for 2001. We forecast for 2002. You see the number of securities here too. So we are making 23 models, actually 22 for forecasting 23 years. So the portfolio we are making is a portfolio that's rebalancing every day based on zero net investment portfolio, equally weighted, and it is for showing the performance for around 22 years. So it's a really long time frame we are focusing on that here. So evaluation data, when we want to test it, as I said, 2000 model for forecasting 2001, 2002. So the 2001 saw the data from 1990 to 2001. So there is no look at bias here. And you see the number of securities and everything. So you have to expect the portfolio, probably you see high Sharpe ratios. It's not reachable in the market with this high, rebalancing every day. You have to pay so much cost and the Sharpe ratios goes away. The point here is not showing a trading strategy. The point here is just a horse race. If a model works well here, it means it's possible to bring it to a better strategy to make profit too. So just focus on that as a horse race at this stage. Benchmark models, large group of models, OLS, Lasso, Ridge, ElasticNet, XGBoost, CatBoost, LightGBM, neural network with different complexities. We made it really competitive because we need a good group of benchmarks to compare these models with it. Otherwise, we are just telling, oh, this model works, this TSFM worked better than that one. It's not enough. We have many models that are easy to even implement it in CPU. Why we need to spend so much money and resources for these models? We have to see. We report accuracy, R squared, overall accuracy, upward, downward, F1. We extend it to portfolio. Portfolio is for the stocks ranked daily by predicted excess return. We are longing top this side, shorting bottom this side. It's equally weighted long-short strategy. We report the results for long and short legs too. It is zero net investment, zero cost. Later we add cost and rebalance daily. As you see, it's quite costly to make something like that. In practice, it's not possible. But here it's just a horse race. The cost, so much. We use Isambard AI supercomputing from UK. We use around 5,000 GPU, 50,000 GPU hours to make all these models. 396 variations of Coronis model, 264 times FM models, and for testing them together, for even benchmark, we have spent 25,000 CPU hours to do all the tests. So it was huge. It doesn't mean anybody, new people, they want to do this stuff, they have to do everything. This is just a really large test in finance. All those ML models, that is conventional in a large, horizon, and many, many models. So it really helps for the next steps when people are ready to understand, oh, this model works better than this one. So it may help. So benchmark models, we test all of them. The interesting thing is that among all these benchmark models at the forecasting level in these 22 years of data, daily data for all US stock markets, they are quite close, but in terms of especially R-squared, these ensemble models, XGBoost, CatBoost, LightGBM, especially CatBoost, they are really good models. And we see this one in machine learning too. In many competitions, these models are on top, passing many, many models. So if you want to choose a really competitive model, CatBoost, XGBoost, especially CatBoost, they are really good models. In paper, we describe how we did fine-tuning. So it's not just setting some parameters. With data, we try to find the best parameters. We applied all the details, ranges are there. So it's not just using them. We try to tune them. So among them, so far, CatBoost. And when we move to Sharpe ratio, I focus on Sharpe ratio. It is high, I know. As I said, this is 22 years of data. daily without, transaction cost, you may reach something like that with anomalies you have in the market and everything. But in practice, of course, it's not possible. So it's just a horse race. And again, when we check the Sharpe ratios, we are reaching the around 6 here for cat boost. And for the other models are quite lower. Like GBM and XGBoost are quite competitive. Again, the same group of models that reaching on top based on all, even based on drop down and everything, all the metrics we showed here. So we choose CatBoost as the benchmark for US stock market because in all tests, it showed really, really good performance. We move to zero shot. So let's move to all time series foundation models that there are many advertisements for them. Every day we see they are changing the world, these AI models. In accuracy, they are fine. Some of them, they are really bad, reaching 49%. In benchmarks, we are around 51%. That makes sense. But here in R squared, they are so bad. In some of them, like times FM is 5,000. It's not even working. So in a real case, you are seeing some sign of, oh, maybe these models are not good as expected. Moving to Sharpe ratio, it's changing Sharpe ratio in many cases to negative. You may ask, what are these 521, 252, and 512? I forgot. We are just using past history of excess return to forecast for each stock for forecasting the next day, So 5, it means we are using 5 days of past history. 21, 25 days of excess return. 252, 252, and 512 is 512. Why we have 512? So this is yearly, this is, weekly, monthly, because most of these TSFMs, the maximum input length, because they are coming from large language models, its max is to 512. This is kind of showing that how much performance we can reach if you use all, window size. So the first thing
So,
you see is that,
Eghbal,
yeah,
I have a small question, and it's there's a few people asking this in the Q&A. So one question says inputs are, you say that you train each year and then you test on the subsequent year. So
yeah,
inputs of that year, let's say 2020 is our first year, they're daily excess returns of all the stocks
in US market.
in there. And
Yeah,
then the output when you're testing is for every stock and every day you get a PDF of or like some distribution of
yeah,
the returns on the next day, right?
yeah,
Or
that's right. Yeah.
okay. And then on top, once you have all these predicted returns, you can compute all your metrics based on
Yeah,
that.
yeah, definitely. Yeah.
And
For
then
here, we are just calculating the average between all those values those models are making. This is common in TSFM. We are not using directly the distribution. It is possible to use it, but we
right.
didn't.
So the average is kind of what you're using, but these windows of 5, 10, 25,
Yeah,
etc., that
yeah,
means you trained your model in 2020, and then every day of 2021, you give it its last 5 days or last 12 days or whatever it is,
yeah, yeah,
ask that
exactly.
pre-trained model what's going to happen tomorrow, and
Yeah,
that's what you use to compute
yeah,
your
yeah.
metrics.
For all models, it's not just for TSFM. For the benchmarks, we did the same. But,
Okay.
TSFMs, they make distribution. That's the difference.
Okay, great. Thanks. I think this
Yeah.
clarifies things.
So yeah, so the first thing we see is that many of them they don't even work. Some of them they reach negative Sharpe ratio. This is our benchmark, the cat boost from the thing I showed you. So all of them, this benchmark model is beating them. Usually they don't work for long, shorter window sizes. This is the same thing we see in large language models. When we provide more information, longer text, they work better. That's why they are increasing the context window for the models as much as possible. Same thing here. For short horizons, five past, for past 5 days, 21 days, they don't work at all. These benchmark models and all other benchmark models, they are usually behaving the same for different, window sizes. Of course, The larger window sizes provide more information, but as you see, for 252, it's reaching the best performance. But here, as much as more, window size, we increase the window size, the performance is increasing. The same thing we see in large language models. The results are clear. None of these models are working. Some of them, they show some performance, but they are much, much lower than the benchmark. So the hype we have that just apply these models without any change, all these models are available from Google, from Amazon, on Hugging Face. None of them are working. And sometimes they're quite dangerous. They are moving to negative Sharpe ratio. Even a simple linear model works better than that. A simple linear model, when I showed you the benchmark, it was much better. Really dangerous. We did the same with other models too. We didn't stop there. Kronos Volt, more, Lag Llama, T-Rex, Toto, Sanda. As I said, IBM, all of them, they are making this model. Flow State, some of them are coming from their universities too. For all of them, we usually saw the same pattern, except few models. Like Toto, one of the new models, it shows really a strong performance. But the reason behind a strong performance can be the really, really large size of these models. It's billion parameters. So much data they use to do that. It's really computationally intensive too to use it because of this size. So we see some models that they didn't even use financial data inside of them, but they are becoming close to the benchmark models we had. There are some promises there that we can see a model that generalize to different tasks too, but still it's becoming close. It's not exactly the same performance. We saw Toto, like Llama, Sandal, and T-Rex. These are the models that are quite competitive, but still lagging behind than the benchmark models. But if I want to go ahead with one model, probably I go with them for financial forecasting. Fine-tuning, it's not helping a lot. We move to pipe tuning, we see most of them, it's fine, same range, but some of them even decreasing the performance, like 49, 48, they are not really good. And again, portfolio performance, bad in many cases. Fine-tuning is not helping. Fine-tuning means with the same data we use for pre-training. For this case, we are using it for just fine-tuning the models that they release. We move to pre-training. It means for these models, as you see, the size of models are smaller. We can make it really like Kronos large with our own data because we were doing 23 models and we didn't have that much access. They made one model. We made like 600 models. So already it's a big, a step. But the first thing we see here is that for accuracy, they are close. But for R-squared are much, much lower. The model is learning something now, except TSFM. But Kronos models are still not as good as, benchmark. But we see some performance benefits. In portfolio, they start working. Again, compared to the benchmark, they are not that competitive, but in some cases, we see really competitive results. So as a model, when we pre-training them with our own data, even in a smaller scale, these Kronos are small, even it is beating Kronos large that the company itself, Google, they release with our own data. So as an architecture, it is good. It is working. It's still not as competitive as, really good models. Again, we use the same hyperparameters they propose. We didn't change it. Later, I talk about that when we play with hyperparameter. But when we deal with these models, like the way we deal with other models, we pre-train or estimate it ourselves, they start working. So far, zero shot, not working at all. Dangerous to use those models. Some models, they are showing some promises that they can generalize data even when they didn't see financial data or not that much financial data. Fine-tuning, not a right claim, at least in this case. Pre-training, models are starting working. But yes, okay, you are starting working, but how much time it takes to pre-train these models? So much. Catboost is already computationally intensive, we know. We need many CPU cores, so it's not, yes, it's working very well, but it's here. For a single model, it takes 20 hours to make. But here, with the large server we had, it's not comparable, the resources you need for this and this. With the, eight, around four H100 GPU, GH200 for each model, even distributed computing, we are reaching 50 hours, 20, 30 hours, but it still is not as competitive as this one. They become quite close, probably. Later you will see. So this is the computational time for pre-training the models. So if we move to the next test, in 10 minutes, I try to wrap it up. The first thing is that the claim behind these models is that you need huge amount of data. Maybe our data is not enough. What happens if we use 94 countries' data together to make these single yearly models? We do the same thing with benchmark models too. What happens? So from, a small amount of data, we are moving to 500 million excess return. And here we are extending the test to another thing. Okay, these models are claiming that you can mix data. What happens if we mix data too with financial ratios and all the momentums, values, investment, quality, size, everything coming from financial report. These are monthly data. They say scale is monthly, but they did the same. They want to test the same too. So we extended global data with JKP factors, 153 factors from Journal of Finance, and we reach around 2 billion samples. We pre-trained the models again. Okay, what if we use synthetic data? JKP is fine, but if I make synthetic data based on JKP data, not based, I mean the same size of the data, and mix it with global. Synthetic data is coming from the way the people in Kronos model, Google, they proposed. We didn't change it. It's coming from some distributions and everything is in the paper, how they made it. So we did it. Global plus synthetic to see whether it is just the extra information is coming from these factors. These models, like large language models, has some learning about and it can link these factors to excess return, or it's just because of the size of data. Any synthetic data can improve the data size. Let's see. So the countries, all of them, they're coming together, 94 countries. It means all data we have around the world, the whole database is coming to make the models. You see the size of data, much, much larger, when excess return, this is global, JKP comes and becomes around 2 billion observations in 2023. Size of data, huge, especially in gigabyte. We are talking about, very small data for US and global, and JPK augmented suddenly increases the size because for each company, we have many factors. It's not like excess return. One company, 1 month, we have many, many factors extracted from the financial reports, and we put all of them inside of these models. So the way we read these tables, plots, this is the benchmark model. The black one is 5 days history. The first gray one, 21, 252, and 512. Same thing here. This group 5, 21, we go ahead. First bar here is the data, the global result. I mean, the data from US. Second one, when we pre-train all these models based on more data with global. Third one becomes the global plus JPK factors. And fourth one becomes global plus synthetic data. How overall accuracy, R squared and F1 are changing. And this one is 50% here, the horizontal line. Let's focus on overall accuracy. It is clear. It's not changing when we are using the low window size, but with higher window sizes, it's clearly improving the performance. And now it is passing the benchmark model. You see here, we are passing the benchmark models. We have more data. It's improving the performance. We didn't see the same improvement in performance with benchmark models. When we have CatBoost, when we have neural network, we added global data. The results are in the paper. Most of them, the performance improved. But these models, because they really have a high number of parameters, more data, like large language models, is improving the performance. Interestingly, when we have synthetic data in replacement for the JPK factors, it's not showing a big difference. Sometimes it's showing better performance than JPK factors. It means these models are mostly hungry for more data. The base model is really important. The base data, you have excess return. It's not like the other models, they mix everything with each other. Here we have excess return in base, but it's possible to bring in future there's some distributions, financial distributions from excess return and improve the performance here. Here it's just some synthetic data from that paper that's not related to finance. So we see we can use JPK factors to improve the performance, but it's not about the nature of that data. It's about size of data. It's time series, and even synthetic data is reaching the same performance. Here, for TSFM, it's changing a model from not working to really working model. And again, it becomes close to the cat poos, and in some cases, better than cat poos. In this case, better than cat poos too. So we see the differences here. Same thing we see in Sharpe ratio. Again, improvement when bring more data. There are differences, but in most cases, improvement, not working to working models and become close, and in some cases, they are beating the best models in the market. During time, how the performance is changing. We have all the historical Sharpe ratios in the paper. This is for cat poos, for all benchmarks we reported. All the models, the Sharpe ratio, these are yearly Sharpe ratios. During time, from 2020 to 2023, they are decreasing, no difference. It's really clear that for all of them, we have a decrease in the Sharpe ratio. So here, if we just focus on 2020 to 2023, probably we reach a Sharpe ratio of 1 or 2, something like that here. At beginning, the performance was much better. 2000, when you use these fancy models, make some good Sharpe ratio, really crazy Sharpe ratios. But now you can't gain that much. But the point here is that when we move to these TSFM, TSFMs, of course, the performance for shorter windows are not good here. For any window size, it is good. For the longer window sizes, better. But here we have, some years that these models, they work very well. Like here, 2022, the beginning of the time these models came to the market. But now it is disappearing again, like here. But still a slightly better performance from these models. You see us, all of them here with different sizes. Transaction cost, when we add it, as expected, it is, destroying everything, disappearing all the Sharpe ratios, daily rebalancing, expected, large number of trades, high turnover. So Sharpe ratio destroying, but still we see more tolerance in TSFMs when there are, there is cost in the market compared to the benchmarks we add. The resilience is higher when we add them. The change is lower, compared to that high value. So, but all of them, even the benchmark models, they are disappearing. This is because of the way we are trading. It's just, as I say, it's horse race. So we presented this one to show those Sharpe ratios in practice, in this context, is not reachable. So 6.5, it's just for some stories. So international markets, we extended the results to not just the US, use the same model to Hong Kong, Taiwan, Korea, Germany, UK, India, same time frame, large number of stocks. This is for inference, just testing the models. We made all the benchmark models for these models, the benchmark models for all these, countries. There are differences between countries. Some countries we see high predictability, like Germany, or Hong Kong. Some of them, none of the models work, like Korea, like India. The predictability, R squared is quite low. For TSFMs, we did the same. And usually we found the same result, same pattern. Shorter window size is not working. Differences between companies. Putting more data in the models improve the performance. In some cases, we are able to beat, benchmark models. In many cases, we don't, as expected, like US market, again, for the Sharpe ratio, for all other countries. This is a really good test. It's not just about TSFMs. We are reporting the machine learning for 23 years of data. all your markets. When we make a single model, how it performs, we can see it here, the Sharpe ratios, Australia, everything. As I said, some countries better, some countries worse. Sharpe ratios for TSFMs, same message usually we got from the US markets. So more countries at inference. As I said, there we use just global. We didn't use the US models for forecasting global market. We use global plus JPK, as you see here, JKP, and after that synthetic augmented. We didn't use the US data to forecast the international market. We use global data. The models pre-trained for that for our forecasting. So hyperparameter tuning is the last touch. Is that, do we really need to follow everything the companies propose? I'm not presenting the results here. You can check it. We played with hyperparameters and we make the models based on changes in hyperparameters too. The same thing we do for machine learning, like CatBoost, Lasso, Ridge, they have hyperparameters. We do hyperparameter tuning. We did the same thing in a smaller scale. And we found that many of the models, we tried to tweak the hyperparameters for them. We thought even increasing the data size, they become sometimes more competitive than larger models. The same message. These are just models. You can make them much, much smaller. You can play with hyperparameter. And before, without increasing model size to crazy hyperparameter, number of parameters, or scaling as much as we did here for testing, you can reach competitive performance, and in some cases, beating the benchmark models in market. We reported all the results in the paper, what hyperparameters we tune, but there are many, many hyperparameters. It's possible to play with that and make these models more competitive. So, generate TSFMs, they don't transfer automatically to finance. We don't have a model that can forecast everything. At least in finance, it's quite dangerous. We see some sign of generalization from some models. So the light is there, but it still needs more working. Conventional models are still competitive. Even linear model works well in many cases. In total, CatBoost, Light GPM, as expected, tree-based models, they work very well. Pre-training really help. Extending data size really help. They make the models more competitive. TSFMs are really sensitive to the window size. We tested until 512. More than this probably makes them better. The same thing we see in large language models. Hyperparameter tuning is really something that we need to look at it more closely to make the models more specialized, scale down, and make them better. They are not dominant. They are not, they need still so much computation to run these models, to pre-train these models, but they are promising. They are going to be promising when we look at these models in the right way, not an off-the-shelf model that is able to do everything. Transformer architecture, the architecture is quite promising, but we need to study them like this paper. We touched a bit to give some directions for the future. So all the models are available. As I said, we are not talking about these models are quite competitive or something like that, but people are able to test them to see how they perform. They can focus on the distributions that we didn't do that to see how, because we can make synthetic data based on these models because they are able to make these distributions, synthetic successes return to pre-train more models. So except, using some synthetic data from outside, we are able to make synthetic data from these models to scale the models. As I said, you can test them. You can download. Code is on GitHub, fintechs.ai, Hugging Face, podcasts, videos, everything is on the website. We are trying to move to multivariate forecasting to make our own models for multivariate and see how these models, they work with the same framework for multivariate analysis. And yeah, that's it. Thank you so much. I tried to make it as fast as possible. Thank you.
So yeah, Eghbal, I think you did a great job. We have another 10 minutes and I've gotten a lot of questions and I'm gonna try to, summarize them. We kind of have a few very like friendly, like how does it work type questions, and then we have a few very critical, like I don't think this will ever work. So I'm gonna start with the friendly ones. And and maybe we could, yeah, I think it's a great idea to keep the QR code so that people can sort of look at, this is one of the great aspects of this research is it's reproducible and people
Yeah.
can go and try it for themselves. So this is a question that I got a little bit curious when seeing your results. Um, and I wondered whether what happens if you train or if you test in sample. So let's say you train in 2020 and clearly Apple stock is in there. And then you tell it, here are 5 days of Apple. Can you predict the sixth day? I
Mm.
imagine that it's almost like a lookup table where it would find the exact price that came afterwards.
Yeah.
But I would be quite curious to see. So, for example, an LLM, I ask it, to be or not to be, what comes after that? And of course, it's going
Mm.
to tell me that's the question. So, in other
Yeah.
words, if I give it 5 days of Apple stocks, surely
Mm.
it's exactly in its training set. So it should with
Yeah.
high, it should be sure and basically it should completely be perfect. And I wonder whether it is as we would expect, or do you
Mm.
think it might do, well, but not that well?
Yeah, I mean that's a good idea. We didn't do this. We just focus on forecasting, but it's really good idea to see how it works in that scale. I expect from the same thing we see in the large language models and we see all other models, it should perform really well. That's my, expectation from the thing I saw. I don't know what is the difference between, these models and benchmarks in that case. It's difficult to answer which one is more, in higher scale is memorizing the data,
Mhm.
but it is a really good, question to test.
Yeah, because I think if we did that with Lasso, it would not, predict the perfect
No,
sixth day.
yeah,
But with this,
yeah,
I suspect it might. Okay, so
maybe.
let me go with the other two friendly questions. One is about how are you doing the Sharpe ratios? Because after all, a Sharpe ratio is a strategy. So do you have a portfolio aspect that sort of creates a portfolio
Yeah. So every
from
day,
your
zero
predictions?
net investment portfolio, like the other studies, rebalancing the portfolio based on the forecasted returns we get for each day from the entire US market. Top decile, bottom decile, zero net investment. We,
Okay.
keep the portfolio for one day. It is, as I said, it's not a practical thing. Nobody can do that. It's just for comparing the models like
Yeah.
other studies they do. Yeah.
Okay, that's great. And the third sort of friendly question I got is, did you use, when you said you augmented the time series data, how does this work? So, for example, are we talking about data like CPI or GDP, like macro data, or are we talking about data related to a stock, like its, ratios or other thing? And I'm
All of them
curious a
are
little bit what
ratios.
this augmenting really
Yeah.
means.
So the JPK factors, they are like the paper is out, the website, you can search for global factors, JPK factors. This is a paper published in Journal of Finance, and they extracted as much as possible factors from financial statements and they put them together at the international level. So you have access to the factors on WRDS now too. So which brought all of them to expand the data size we have. As I said, this is a data mining thing. The model there's no structure. These are just more added information to the models.
Hmm.
Yeah.
So
And the
it's not
scale.
that you're very carefully feeding it the data related to
No.
when
So all
the.
these TSFMs, the point here is that add as much as data you like for pre-training without caring what it means. We try to do the same thing. We are not telling it's a good idea. We are testing it.
Hmm. Hmm. Okay. All right. Well, in the last 5 minutes, I've got the more critical ones, but
Mhm.
sometimes you learn a lot from the
Yeah,
critical
definitely.
feedback. So the first one is encode. It's broad. It's is encoding of time series in the same nature as encoding of text. Is the encoding of a time series of a numerical random variable different than text? In other words, a numerical variable is naturally a vector with a notion of length
Yes.
and distance, while
Yeah,
text maybe length and distance is a bit more abstract. So
definitely.
I guess
Yeah.
how do you think about that difference
So
philosophically?
first, I'm not supporting these models. The way they are, they are coding the data. Definitely, that's the right comment. The way we are dealing with numerical data with those benchmarks is much, much better than the way we deal with the numerical data with TSFM because they're translating numerical data to textual data to feed it to the models. And that's not really good. Definitely, we are losing some information. The point is that there are some features these models they have that they make them interesting. This is the bottleneck. At the same time, these models they are quite scalable. The same thing we see in large language models. Usually we can pre-train or test a model with the size of data for a conventional model like CatBoost. The models I was, presenting there with CatBoost or Light GPM, it took days, sometimes, around 1 month to run them on some CPUs. It becomes quite computationally intensive to run them. But these models, like large language models, if you have good access to hardware, you can scale them so fast. Some benefits, but as you said, some problems too. Definitely, I agree with you. And I'm not supporting these models. I'm testing, showing even they are not working. I'm not telling that they work. I'm just telling this place is not working. This place is promising. And finally, I just reached a promising term. It's not competitive. It's just promising. Many problems in this part of translation. We are losing so much information, but architectures are becoming better too. If you check the latest models, they try to manage the problem you were raising to make the models that directly read this numerical data without those conversion in the middle we saw in the Kronos model.
Mhm. All right. So the next question is maybe the more critical one, and I'm curious how you think about this. So he says, I do not believe a foundation model can work for financial time
Mm-hmm.
series as the domain is not finite. In
Mm-hmm.
NLP or text data, the number of words and sentences are finite. There are an
Yeah,
infinite amount of distribution causal relationships.
yeah,
And second, the data in finance is noisy. The
mm-hmm.
size of the model is not relevant as long as the
Yeah,
input do not carry information too. As
that's
opposed
right.
to text, each input is extremely noisy. What are your
Yeah.
thoughts about that?
I agree. Yeah, I presented this idea because I wanted to show these models are not working. So at the off the shelf, that you mix all data with each other, make a single model, it was not working. In many
Mhm.
models, it was not working. Many of these models, they spend million or million pounds or dollars for training these models at the company level. It's not working. So it was the main message actually we wanted to convey that be careful, don't use off the shelf models when it comes and there's so much marketing behind that. There may be something there that we found is there. Architecture is promising. 95% of these models they didn't work. Even if they showed working, it was in a really, really large scale, billions of parameters. That is not even, feasible to use some of these models in that scale. It doesn't make sense to use that because the simpler models work better. So actually, the message you were talking about that is the same message we talk about that here. It is still experimental, everything we talk about it here. Same message, not working, right? Fine tuning is not helping. But as an architecture, it can be promising if we try to tune the architectures. We are using it like the architecture of CatBoost, like Light GBM. It's possible to do that. But it shows, if you check the paper, and finally we are like stressing that it's even dangerous to use these models off the shelf.
Hmm. Yeah, I think that some people may have misunderstood you as like a complete blind supporter of all LLM art technology, when in fact it seems like you have a critical you
Yeah,
know,
yeah, yeah, yeah.
and
Totally. All
the
the
last
newspapers are quite like critical. Yeah.
The last question does this a little bit. First, they say, thanks, Eghbal, for your great and rich presentation. And then, why do you believe TSFMs or large language models work for time series forecasting? So, maybe you're not as strong a believer as
Yeah.
the person seems to think. But at the end, it is just another way of thinking of autoregressive relationships. However, in finance, with the time series, are affected by tons of other exogenous variables and
Yeah.
events. How do you
Yeah.
consider them in TSFMs? So
Yeah.
maybe this is related to the augmenting of time series question.
Yeah, but I think he's mostly talking about the multivariate because all the models we talk about that they were univariate because language is univariate. LLM is univariate. It's not multivariate. So we are just for, training the model with huge data forecasting next word for a single sentence or to, input. Multivariate is a new trend we see in these models. Last few months, last year, you try to release multivariate model that at the same time you can insert your input, few variables, different variables to forecast something. This is really new. Again, it's really this one that I presented today is started from few years, but the multivariate area is few months, old, or maybe 1 years old. They see it works. They have some tweaks in the model, these companies, to show it's working. It's so early to say. It is a good direction. I'm gonna go into that direction to see how it works. But as I said, all of them are still experimental. I'm not supporting these models. I'm not totally against them. Mostly I'm against them if you want to show my side that at least off the shelf. But there are, as you see, like this point, there are many directions for improvement in these models. Maybe finally we find even the conventional models as we present and they works better.
Okay, well, Egbal, thank you very much,
Thank
especially for the all your honest answers to questions that were a bit tough,
you.
I really appreciate this. So thanks again
Yeah,
for
thank you.
coming to our seminar.
Thank you so much for the invitation. Thanks all the participants and for the questions too. I'm happy to answer any questions. Just send me an email and yeah, you can check my website here if I find it.
And are the slides available on the website?
No, because these days I'm presenting this for different places, but probably in the next few months it's going to be available. But as I said, the paper is quite, at least this version, it's many, many pages and many details. So everything
Great.
is there.